A very good morning to all. Dear students, welcome to my new section. In this section, we are going to discuss about a black box method of machine learning, that is support vector machine. So, in the previous module, we will discuss about neural networks. In that module, I have already said that the support vector machine and neural networks are two examples of black box methods of machine learning. In this module we will discuss about finite dimensional vector spaces, hyperplanes, support vector classifier, kernel methods, Gaussian kernel, and multi-class SVM. These are the contents of the fifth module. So coming to a support vector machine, or in short SVM. It is a supervised machine learning algorithm. It can be used for both the classification and regression applications, and it is a black box method of machine learning. Support vector machines. A support vector machine, or SVM, can be imagined as a surface that creates a boundary between points of data plotted in multidimensional space that represent examples and their feature values. The goal of SVM is to create a flat boundary called a hyperplane, which divides the space to create fairly homogeneous partitions on either side. The SVM learning combines the instinct-based nearest neighbor learning and the linear regression modeling approaches, which we are discussed in the previous module. This combination is very extremely powerful, and it will model highly complex relationship in the real-world data. The support vector machine can be adapted for use with any type of learning task, such as classification, numeric prediction, pattern recognition, etc. Now let's see what are the different applications of support vector machine. The three main applications of support vector machines are gene expression data classification, text categorization, and the detection of rare yet important events. Hyperplanes. Hyperplane is a boundary which partitions the data into groups of similar class values. The support vector machine, or SVM, uses hyperplanes to partition data into group of similar class values. So this is a pictorial representation of a flat boundary which will separate the two classes of objects. So this blue circle and red circle is classified by using this flat boundary. So for example, the hyperplane separate group of circles and squares into two and three dimensions. Consider these two figures. This figure represents the two-dimensional classification, and this represents the three-dimensional classification of objects. In this diagram, this is the hyperplane. This hyperplane will separate the group of the circle objects and the square objects into two classes or two groups by using this hyperplane or straight line. Whereas in the case of this three dimension, this circle objects, circles and squares are classified by using a flat surface. Now let's see what is the term linearly separable means. In our example, the circles and squares can be separated perfectly by the straight line or a flat surface. They are said to be linearly separable. So, linear separation is nothing but these two objects can be separated by using the straight line or a flat surface. Then we can say that they are linearly separable. In two dimension, the task of the SVM algorithm is to identify a line that separates the two classes. So consider this figure, which classifies the squares and circles into two different classes. Okay, so in between these two, in this figure, we can see that different lines are there to separate these two classes. Okay, line A, B and C are three such possibility, three lines which will separate the squares and circles into two different groups. Okay, that is more than one choice of dividing the line between the groups of circles and squares. Three such possibilities are there: line A, B, and C. Now our question is, how does the algorithm choose the best option? In which of these this line A and line B and line C, among these three lines, how the which line the algorithm choose? Okay, the answer is the algorithm will choose the maximum margin hyperplane among these hyperplanes. A, B, and C are hyperplanes which will separate the objects into two classes of objects into two different groups, and the hyperplane which separate these two classes is known as the maximum margin hyperplane. Okay, the algorithm support vector machine SVM classifier chooses the maximum margin hyperplane for the classification. Now let's see what is a maximum margin hyperplane, or in short we call it as MMH. MMH. Okay, the maximum margin hyperplane creates the greatest separation between the two classes. It generalizes the best of the future data. It improves the chance that in case of random noise, the points will remain on the correct side of the boundary. This is a pictorial representation of maximum margin hyperplane. Okay, this here there is circles and squares are there, and they are classified into two different groups, homogeneous groups, by using the maximum margin hyperplane. These are the margin between these two group of data. This is another schematic representation of a maximum margin hyperplane. In this diagram also, two classes of objects are there: stars and circles, red circles, and this is the maximum margin hyperplane in between the maximum margin or maximum margin hyperplane between the two class of objects. This is the class 1 and this is the class 2. So in this diagram, the maximum margin hyperplane is clearly represented in this diagram, and this margin will separate the circles and squares into two different two different groups. And we can see that in this figure, the objects or the examples which are closest to the maximum margin hyperplane is known as support vector. Okay, in this diagram it is clearly indicated that there is a support vector. The support vector is nothing but it is the examples or objects which are closest to the maximum margin hyperplane. So now let's define the support vectors. The points from each class that are closest to the MMH maximum margin hyperplane is known as support vectors. Each class must have at least one support vector, but it is possible to have more than one support vector. Using the support vectors alone, it is possible to define the maximum margin hyperplane. This is a key feature of support vector machine. So this is the objects which we are going to classify. This is one possibility of hyperplane which divides the data into different two groups. This is another possibility of a line or a hyperplane which divides the two objects into two different classes. This is another possibility. So many possibilities are there. Any of these would be fine, but we will choose the best option. That best option is the maximum margin hyperplane. So define the margin of a linear classifier as the width that the boundary could be increased by before hitting a data point. So consider this diagram. Different hyperplanes are represented in this: H1 hyperplane 1, H2 hyperplane 2, and H3 hyperplane 3. Here in this diagram, two class of objects are there: black circles and white circles. In this figure, it is clear that the hyperplane H1 does not separate the classes. Hyperplane H1 does not separate the classes into two groups. Whereas the hyperplane H2, it will separate the classes into two groups. It will separate the classes into objects into two different classes, but only with a small margin. Here there is, we can see it is clearly represented that H2 will separate the data into two different classes, but there is only small margin here. Consider the case of a hyperplane 3 or H3. This H3 separate the two class of objects with the maximum margin. So we will choose the H3 as the maximum margin hyperplane. So the support vectors. Example which is closest to the hyperplane are support vectors. The margin rho of the separator is the distance between the support vectors, which is clearly indicated here. So these three are the support vectors, which is represented in this diagram, and rho is the distance between the support vectors. So now let's see how to find out the MMH, maximum margin hyperplane, in the case of a linearly separable data. So first option is convex hull. So convex hull is the outer boundaries of the two groups of data points that are known as convex hull. So the first option is the maximum margin hyperplane is the perpendicular bisector of shortest line between the two convex hull. Sophisticated computer algorithms that use a technique known as quadratic optimization are capable of finding the maximum margin in this way. This is the schematic representation of the of finding the maximum margin hyperplane in the case of a linearly separable data by using the first option, that is by using the convex hull. So according to the first criteria, the maximum margin hyperplane is the perpendicular bisector of shortest line between the two convex hull. So we first of all we determine the convex hull of the two different classes. This is the first convex hull, and this is the second convex hull. Okay, so convex hull, first determine the convex hull, then find out the shortest distance between the two different convex hull, and by drawing the perpendicular bisector of this shortest distance between the convex hull, we will get the maximum margin hyperplane. So the method is that first of all find out the convex hull of two classes, then find out the shortest distance between the two convex hull, and draw the perpendicular bisector of shortest distance between the two convex hull, and thus we will get the maximum margin hyperplane. The second method is second or an alternative but equivalent approach involve a search through the space of every possible hyperplane in order to find a set of two parallel planes that divide the points into homogeneous group, yet themselves are as far apart as possible. Okay, so to understand the search process, we will need to define exactly what we mean by a hyperplane. In an n-dimensional space, the following equation can be used for representing a hyperplane. Okay, the equation for representing the maximum margin hyperplane is w dot x plus b is equal to 0. Here the arrow marks are indicated which is used for indicating vectors rather than a single number. These w and x are vectors, not a single number. For example, w is a vector of n weights, that is w1, w2, etc. wn, and b is a single number which is known as bias. The bias is conceptually equivalent to the intercept term in the slope-intercept form. Using this formula, the goal of the process is to find a set of weights that specify the two hyperplanes as follows. Okay, so the goal of the process is to find a set of weight that specify we have to determine the two hyperplanes as follows. So w dot x plus b greater than or equal to plus 1 and w dot x plus b less than or equal to minus 1. These two equations represent the two hyperplanes. Okay, w indicates the weight vector, x is the input vector, and b is the bias. This is the schematic representation of a maximum margin hyperplane, where wx plus b is equal to minus 1 represent a hyperplane, and wx plus b is equal to 1 positive 1 represent a hyperplane, and this is the central line which indicates the wx plus b is equal to 0. Okay, so this x1 and x3 will represent the two parallel hyperplanes which are far apart as possible. The hyperplanes are specified such that all the points of one class fall above the first hyperplane and all the points of the other class fall beneath the second hyperplane. This is possible so long as the data are linearly separable. So the distance, according to this method, the distance between these two planes is d is equal to 2 divided by cardinality of w. So W is the Euclidean norm or the distance from the origin to the vector W. So in order to maximize the distance, we need to minimize the value of W. So that